So today I'm going to explain how to interpret linear graphs, and by the end of this you'll be able to interpret them in the context of the problem and write equations to fit them. So it is important to know the definition of the gradient or the slope, and it is the rate of change between any 2 points on a line. It is also referred to as the rise over the run. It measures the steepness of a line. So the larger the gradient or the slope, the steeper the line is. And the rate of change is important to know as you're moving into word problems. So here's an example of just a graph and a line through it. It is important to know that each of these notches on the graph represents 10 units. So you can see this would be x is 10, x is 20, x is 30, and so on with the y-axis. So when you're wanting to know the slope, which is the rise over the run, you want to count the vertical distance and the horizontal distance between any 2 points that are on the line. So, for example, if you choose these 2 points, so the y-intercept, which is at negative 100, and then this point right here, which crosses through at negative 80 for y and 20 for x, so the point 20, negative 80. If you count the change in y and then the change in x, you will notice that to go from negative 100 to negative 80, that is an increase, a vertical rise of 20 units. To go from 0 on the x-axis to 20 on the x-axis, that is a horizontal change of 20 units. So the rise and the run are the same in this example. So the slope would be 20 over 20, the rise over the run, which simplifies to 1, so a slope of 1. If you're wanting to find the y-intercept, that is the point that the line crosses the y-axis. So the point that it crosses here is at negative 100, so your y-intercept is negative 100. The last part is just to write an equation that fits this graph. So in slope-intercept form, where you're using the y-intercept and the slope, the format is y equals mx plus c. So your m is your slope, which was 1 in this example. Your c is your y-intercept, which is negative 100. So you would write the equation as y equals x minus 100. You can pause the video and look at a few other examples. So here's another linear graph. Notice that again, the x-axis and the y-axis is increasing by tens every time. And notice that the y-intercept is right in the middle of 10 and 20. So it's actually a y-intercept of 15. When you're choosing points on this line, I would choose points that cross through at nice spots, like the intersection of x is 10 and y is 20, or at the point x is 30, y is 30, to count the rise over the run. And you can pause the video to jump ahead on this. Here's the answers for those. Here's another graph. Notice the x-axis, it's increasing by 100 every time, and the y-axis is increasing by 100 every time as well. So when you're counting the rise over the run, you need to keep that in mind, that every 1 unit increase in the y or in the x direction is actually an increase of 100 units. And again, you can pause the video at any point just to see how it's worked out and the equation that fits the line. Now getting into linear graphs and understanding and interpreting linear graphs. So here's an example, and this graph alongside indicates the distance run by a sprinter in a number of seconds. So on the x-axis, you have time. On the y-axis, you have distance. So you can see that each increase in seconds is also an increase in the distance covered, which would make sense in the context of the problem. The more you run, the longer you run, the longer your distance is. So we need to interpret the gradient, we need to find the gradient, and we need to explain the speed if it is a constant variable and what evidence tells us that it is a constant speed. Well, speed is always the rate of change, and the rate of change is the distance over the time. So meters per second. So how many meters does the runner cover in a certain number of seconds? Well, if you find the rate of change, the distance between any 2 points on this line, you will notice that this is a line and it is a constant rate of change. So it is the same steepness throughout the entire portion of the line, which answers question C. The speed is constant. If it were not constant, you would see little divots, ups and downs, and flat lines, to show that over time the distance is either less distance or more distance, or the distance is not increasing whatsoever, yet the time is increasing. But we can see that this is a constant rate of change.